So in this pre-lecture vodcast, I'm going to be talking about synapomorphies and how we can use synapomorphies to construct phylogenies. So first of all, a synapomorphy is a derived character that is shared by a common ancestor and its descendants. And so in the previous vodcast, I was talking about monophyletic groups, or clades. So often you'll see that a common ancestor within a monophyletic group will possess some character, and all of its descendants will also possess that character. And that should be quite intuitive. So in this example, what we're looking at, it's from your text. It shows the evolution of tetrapod traits and how they evolve slowly over time, and comparing them to our bony ray-finned fished ancestors. An example of a synapomorphy in this phylogeny is now highlighted within a red box. A shared derived character that is shared by this common ancestor of everything from coelacanths to all living tetrapods is the single basal element that connects the fin or limb to the rest of the body. The red box in this picture shows that bone on a lobe-finned fish, the coelacanth. And we also have that bone, but it just looks really different. It's actually our humerus. So we share this trait with all other animals that descended from that common ancestor who originally expressed this bone. Now, become familiar with the term synapomorphy because I promise it will be used a lot during the diversity section of this course as we attempt to describe shared characteristics of all organisms within a certain taxon. So, how do you construct trees and understand relationships of groups of organisms, like that of a seal or this bobcat, if you can't just go back in time and observe the relationships as they happened, as these speciation events happened? So we really have limited information, right? Like we have the living organisms themselves, we have fossils if we're lucky. But thankfully, you can exploit the fact that we have groups of organisms that share traits due to their descent from a common ancestor, right? So you can use what's called a table of synapomorphies as a way to reconstruct a tree based on traits of living organisms. So let's use these two mammals in front of you as an example. They're both from the clade called carnivora. A trait that they share with one another, and all carnivores for that matter, are these carnassials, which are teeth highlighted in blue and red above, and they're used for shearing meat. So let's take a look at some other traits. So we can look at other characters and character states within carnivorans. For instance, let's focus on character number 6, tails. Some carnivores have an elongated tail, which is the ancestral state, and some have a short tail, which is a more derived state. Now, when I say derived, I mean it's a character state which exists in the present organism and is altered from the ancestral condition. So let's build what's called a character matrix for carnivora, with which we can construct a phylogeny. So the taxa are along the vertical axis of this character matrix, and the character numbers, which correspond to the character states in the first image, are along the top of this matrix. The first row describes the character states of the lemur, which serves as our outgroup. So lemurs are a suitable outgroup in this example because they're closely related to carnivorans, so they are both clades within mammals, but they're primates. So that's why there are zeros across the top of the matrix that correspond to lemurs, because they're our outgroup. So now you can go through all the different taxa and fill out the data matrix with zeros if that group possesses the ancestral state, or a 1 if they possess the derived state of that character. Once you've filled out your data matrix, you can look for taxa that share derived character states, and clades will begin to emerge. Your main objective when you do this is to construct a tree with as few character state changes as possible. So in the tree above, there are 12 changes that correspond to the 12 characters from the original matrix. Of course, phylogenies are not always this straightforward, and you'll see some interesting examples of exceptions to this in class. In the phylogeny above, you can see that seals and walruses are the only two taxa, for instance, that have number 1 for character states 11 and 12, to the exclusion of all other groups. And so they're probably placed together on that tree because they share this common ancestor who also possesses those derived traits. So we will continue this topic in class, so stay tuned, and we'll see you then.